Good afternoon and welcome to today's electronic design webinar, Designing Next-Gen Bluetooth Low Energy Systems for the Internet of Things, sponsored by Cypress and Digi-Key. I'm Bill Wong, Technology Editor with Electronic Design. Let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. We welcome your questions during today's event. Just type your questions into the question window on the side of the screen and then hit the submit button. We will answer as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time. Please also be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. You may also download a PDF copy of the slides by clicking on the green folder icon in the toolbar beneath the slides. Now let me introduce today's speaker. Gagan Luthra is a product marketing manager at Cypress Semiconductor Corporation, working on the PSoC platform of Programmable System on Chips. He started working with Cypress as an intern in 2005 while studying electrical engineering at Washington State University. He's passionate about embedded solutions and the engineering hobbyist community, small form factor and real-time computing, DIY projects, the maker community, digital audiovisual art, and more. Now let me turn things over to our presenter. Gagan, the floor is yours.
Thank you so much, and good day to everybody. Gagan Luthra from Cypress Semiconductor, and I'm here today to talk about a very exciting topic, which is Bluetooth Low Energy. And specifically, I'm here to introduce a product by Cypress called PSoC 4BLE. PSoC stands for Programmable System on Chip, and several of you may already be familiar with this platform of microcontroller-based products. But for those of you who are not, I'll go into some of the details of it today. And BLE is an acronym for Bluetooth Low Energy. So with today's webinar, we will learn how we can use this PSoC 4BLE solution from Cypress Semiconductor to easily design wireless systems that are also low power, but extremely highly integrated for all of your next generation consumer products. So let's get started right up. So the Internet of Things is a term that we've very commonly hear in the industry today. What does it really mean? At its essence, Internet of Things talks about connectivity concepts through the Internet or through gateways that previously only existed on computers and cell phones, but now is being translated to everyday physical objects. For instance, my coffee mug may have some sort of sensors and connectivity so that it can tweet its own temperature and the likes of that. We see more realistic examples in maybe home automation where my thermostat is linked up with the rest of my home and eventually to the internet. So really the message here is the IoT that started as a concept has really turned into a commercial reality. There's a lot of new and exciting products in the market, be it in the consumer space or even in the industrial and infrastructural space, and they're only growing faster every day. And to create an IoT product, if you break it down into the smallest of the building blocks, you need a system that's capable of sensing the environment around it, and it does this with the help of sensors for temperature, blood pressure, moisture, so on and so forth. In addition to these systems being able to sense the environment around themselves or the person that they're on, they need to be able to act autonomously and make some decisions based on that sensor data, which typically requires some sort of a computing device like a CPU. And then all of these systems are interactive, which means they communicate with each other or onwards to a cell phone or an internet server, for which they typically require wireless or wired communication standards. More often than not wireless, because these products are small and portable nodes that are deployed wirelessly, untethered, running on batteries. So not only is it nice to have these products be wireless, but it's very important for them to be low power consumption so that they can last for a long time on batteries. And because of many of these reasons, Bluetooth Low Energy has slowly but surely emerged as the standard for IoT products, especially in the consumer space. There's a couple of reasons for it. One of the reasons being that Bluetooth as a technology is very ubiquitous. It's much easier to finish the other side of the communication because our cell phones, laptops, and tablets, and even TVs and so on already have Bluetooth technology built into it. So when I create a new product like a fitness monitor or a smartwatch that talks BLE, it can already communicate with my cell phone or tablet very easily. In addition to its ubiquitous nature, BLE or Bluetooth Low Energy from the ground up was architected and designed to be an extremely low power technology. It's different from the classic Bluetooth in terms of the type of data it carries, the amount of data it carries, and it was designed, again, in mind for carrying sensor data or status information from these nodes and communicate onwards to other nodes around it. So the gist of this slide really is that IoT products are rapidly being deployed in the industry. There's a lot of commercial activity behind it, and Bluetooth Low Energy is an ideal choice of wireless communication for these IoT products. And here's a couple examples of the type of IoT products we've seen in the market over the last couple of years or so. Obviously, those fitness monitors, pedometers, and so on from the likes of Jawbone, Fitbit, Misfit, and so on. Other products like smartwatches or health and fitness monitoring devices like heart rate monitors from various other companies. And beyond the health and fitness and the consumer space, we've also seen some interesting applications in the home automation space or in the industrial infrastructure space, where you could have things like your deadbolt now be replaced or added with Bluetooth Low Energy options, so you can unlock your front door with your cell phone and not just your key. So it's an exciting time and for all of us in this IoT space, and lots more to be seen. So before I dive right into the PSoC for BLE solution, I quickly wanted to cover a few terms on Bluetooth, the technology. So Bluetooth Classic is the Bluetooth that we've all used over the last so many years, and this is the Bluetooth that's built into our cell phones and enabled communication like using our cell phone headsets or talking through our car speakerphone and so on. So that technology now in today's day is referred to as Bluetooth Classic. It refers to the older Bluetooth technology that's existed for a while. Bluetooth Low Energy is the new standard of Bluetooth that was introduced in 2010. Now, even though Bluetooth Low Energy and Bluetooth Classic operate in the same frequency band of 2.4 gigahertz, they're architecturally different, and BLE is not backwards compatible with Bluetooth Classic. So that's an important distinction to remember. One of the main differences you'll notice between BLE and Bluetooth Classic is that BLE can only support up to a 1 megabit per second data rate, which is reduced and less than Bluetooth Classic, which could do up to 3 megabits per second. And again, this goes back to the standards being architected for different types of data that they're carrying. So Bluetooth 4.0 is the version of the Bluetooth specification that introduced the BLE standard, or the Bluetooth Low Energy standard, and this came out in 2010. Since then, there's been a couple improvements or enhancements to the spec already. In 2013, Bluetooth 4.1 was released, which improved some of the security and power consumption features of the spec. And late last year, Bluetooth 4.2 was introduced, which added more features like even more increased security and privacy, but also some increased packet length, so you could transfer some additional data bytes over the Bluetooth low energy radios. So it can be a little confusing, especially if you're looking at BLE for the first time and still thinking in terms of classic Bluetooth. But the Bluetooth Special Interest Group, or the Bluetooth SIG, which is the organization that defines the Bluetooth spec, creates the standards, and helps with certification and testing, has created a couple of marketing brands to try and ease that clarification of the different Bluetooth standards now. And the terms used are Bluetooth Classic, Bluetooth Smart, and Bluetooth Smart Ready. So again, Bluetooth Classic is your old Bluetooth products like the cell phone headset here on the right side of this slide. Your Bluetooth Smart product, which are the products that we've seen introduced over the last couple of years, are products that can only communicate over Bluetooth Low Energy. So these are your new fitness monitors or your new smartwatches that can only talk the Bluetooth Low Energy protocol, and they are referred to as Bluetooth Smart products. And then all of the new cell phones and tablets and other host devices that have come out in the last couple of years are capable of talking to both these devices. Your cell phone today, your iPhone 6, for example, can continue to talk to Bluetooth Classic headsets, but it can also talk and connect with the new fitness monitor Bluetooth Smart devices. So a product that can support both these standards is called Bluetooth Smart Ready. So in summary, those are the three marketing brands or marketing names that you have to keep in mind when referring to Bluetooth. You either create a Bluetooth Classic product, or a Bluetooth Smart product, or a Bluetooth Smart Ready product. All of the discussion in today's context with BLE is going to refer to creating Bluetooth Smart products only. So the likes of the fitness monitors, the likes of the smartwatches, and so on. So when designing IoT products, as I mentioned, the ones that need sensors, need some sort of computation, and then need wireless communication to communicate with other nodes, we as engineers face certain challenges today. The first one being that creating a wireless sensor-based system, a system as defined itself, is difficult. When you have sensors added to your system, when you have wireless communication capabilities added to your system, what you often end up doing as a hardware engineer is working with multiple ICs from multiple vendors. You need different chips. Maybe one is a microcontroller, one for wireless communication, a few more to interface with your sensors. So your system is complex because of the number of chips involved in it, and so on. The wireless side of these IoT products, specifically Bluetooth Low Energy, is complex as well, especially if you haven't done any wireless development in the past. Wireless technologies have pretty stringent protocol requirements, very specific language that they speak in, and all of that can get pretty complex from a firmware development perspective. And then on a board level, on the PCB level, the actual RF communication over your Bluetooth antenna can also be tricky, again, if you don't have the expertise and the experience having done it before. So that's the first level of challenge. Because of some of these challenges, like having to design with multiple ICs and use multiple chips, it becomes difficult to keep your product costs down because you are working with multiple ICs. It also becomes difficult to keep the product size down because obviously the more number of chips you have on your PCB, the larger your board size would be. So size and cost becomes a challenge in a very competitive market where you're able to buy fitness monitors from Asia for less than $20. So your margins as a hardware manufacturer become very challenging as well. And most importantly, the biggest complaint with the first generation of these IoT products, especially the likes of smartwatches, has been power consumption. These products are running off of batteries and they're not lasting too long today, so consumers are not very happy with the usability of such products. So over the course of today's presentation, I will show you how Cypress's solution for Bluetooth Low Energy, which is PSoC 4 BLE, solves these challenges in a few different ways. And I won't read the slide here. I'll get right into the specifics of the solution and how it can help you overcome these challenges. PSoC 4 BLE is a one-chip solution, and the solution has a software front end called PSoC Creator. PSoC Creator is a free development IDE from Cypress that is used to create any sort of PSoC systems. And PSoC Creator works in a very graphical or schematic capture-based paradigm, similar to an FPGA for those digital engineers who are familiar with that paradigm. Instead of working with a microcontroller that has fixed function peripherals around it, assigned to certain registers in a memory map and locked down to certain pins, PSoC is more of a programmable fabric that gives you, the engineer, the power to design the chip the way you need to. And you do this by dragging and dropping pre-built components, which are essentially hardware IP blocks that Cypress creates for you and offers through the tool PSoC Creator. You drag and drop these components onto your schematic, as you can see on the slide here, and wire them up to create a system. So at this point, what you're doing is you're defining at a chip level what your system will do from a schematic view. It helps you design the way you think. It helps you design, what you see is what you get sort of a system. But it doesn't stop there. Once you've done the hardware configuration of a specific PSoC chip and define the hardware in the way you want your system to work, the tool then generates a set of APIs for each of those components that you have on your schematic. And then you can go into your traditional firmware development, which is get into the code editor and write C code, embedded C code in your main.c file that the CPU would execute. And the fact that all of these component blocks are augmented with APIs that Cypress provides for you, as a firmware developer, your job becomes much easier. You simply use those APIs to have the system and the application do what it's intended to. And all of this is supported by thorough documentation and data sheets and example projects to help guide you through all of these steps. Just like we have components for all of the IP blocks inside a PSoC chip, like the analog systems like an ADC, or the digital systems like a timer or a PWM, the Bluetooth low energy block inside a PSoC chip is also exercised through a component that you can drag and drop onto your schematic. This component includes all of the hardware controllers to talk to the Bluetooth low energy block that resides inside the chip. It also includes the Bluetooth 4.1 or 4.2 version of the protocol stack, so all of the communication protocol is also included, and it provides you a graphical-based configurator to set up your Bluetooth profiles, to configure the specifics of your Bluetooth stack, like your security settings, your connection settings, and so on, instead of having to do it in several lines of code. By simply filling in the blanks in a graphical box, or choosing and picking from a drop-down list in a menu, you can select what type of a Bluetooth device you're trying to create, what specifics on the Bluetooth stack you need to configure, and the tool then generates all this configuration code for you, saving you the time and effort of having gone through hundreds of lines of code to implement all of this. And at the end of the day, once the code is generated, you have simple APIs again to exercise the stack or to do the actual communication between this Bluetooth low energy device and another BLE or Bluetooth device on the other end. So the wireless protocol and stack part of Bluetooth low energy is greatly simplified by using this pre-built component inside PSoC Creator. On the PCB side of things, or at the board level, things are also simplified when you use PSoC for BLE. There's a concept of a balun, which is a play on words for balance, unbalance. It's a circuit that goes between your antenna and the chip, and that helps go from a single-ended signal to a differential or vice versa. Essentially creates your antenna matching network so that you have the best performance out of your radio. Creating such a system in the antenna matching network requires this thing called balun, and there's a couple ways to add a balun to your system. You can either go build one out of circuitry, which requires 7 to 8 passive components, and then you have the challenge of tuning each of these components to get the best performance out of it, which can be complex and time-consuming. Or you can spend the 20 to 40 cents to buy a balun chip and simply attach it between your antenna and your microcontroller. But then, of course, that adds cost to your system, and it also increases the amount of board space that you are taking. With PSoC for BLE, the balun is actually integrated inside the chip, so creating an antenna matching network is extremely easy. Hooking up to a standard antenna is extremely easy. All you need is two external components, specifically a capacitor and an inductor, as opposed to up to 7, 8, or 9 with other solutions. So the board level of your design is greatly simplified as well when using PSoC for BLE. Now, PSoC is different from a microcontroller because it has various degrees of freedom in terms of the flexibility around the chip and also the IP blocks that are available inside of it. And because of this, PSoC for BLE offers you a highly integrated solution that allows you to create entire IoT systems with a single chip. Specifically, PSoC for BLE integrates technologies like CapSense, which is capacitive touch sensing, and also analog blocks that help you create analog front ends to interface with any type of sensors without having to buy a separate sensor chip. For instance, if I wanted to create a heart rate monitor, today, I have the option of buying a heart rate monitoring chip and spending a dollar or two on it, or I can create one using analog components, off-the-shelf analog components like op-amps, comparators, ADCs, analog muxes, and so on. But with the PSoC, for BLE, you have all of these blocks, analog blocks, available inside the chip. And just like I showed you in the first slide with PSoC Creator, you can drag and drop those op-amps, those comparators, those ADCs, and those muxes onto your schematic and wire them up in a way such that they represent that circuit that you would make outside of the chip or from another IC that you would buy. You could implement that entire analog front end for a heart rate monitor sensor inside a PSoC, and all it would need on the outside would be the actual electrodes and maybe a few passive components like a resistor and so on to attach to the chip. This greatly reduces your BOM cost. This greatly simplifies the design because you're not using multiple chips, you're using only one chip, and allows you to really create those small form factor integrated systems. In addition to the analog and the capacitive touch sensing, PSoC for BLE also has a digital fabric that's completely programmable. This is a CPLD-based digital fabric where you can either exercise by using pre-built components that Cypress provides in the library, or by even writing your HDL or hardware description language in Verilog inside of PSoC Creator. So think of it as this separate fabric of the chip that's very well integrated with the CPU and the memory and allows you to exercise some deterministic hardware control and communications inside the same chip. So at the end of the day, what you get is a very tightly packed, highly integrated system that offers a microcontroller, which is an ARM Cortex M0 core at 48 megahertz, a Bluetooth low energy radio inside the chip with an integrated balun, a whole lot of analog components like an ADC, op-amps, comparators, and muxes to create analog circuits that eventually act as your sensor interfaces, and another set of digital fabric that allows you to create any sort of other custom peripherals or control systems, all integrated inside a single chip. And all of these are programmable over and over again. You can keep designing them, keep changing your design, and hit a single button in PSoC Creator to program the chip with the newest design. And you can do this process iteratively till you get the perfect chip that you're designing. And this schematic, or this screenshot here below that I just pulled, is a screenshot from PSoC Creator of the schematic, and it shows you how, using the single PSoC for BLE chip, we've been able to construct an entire heart rate monitoring product. Starting from the left, you see your electrodes for a heart rate monitor coming in, going into my analog front end, which is constructed using 4 op-amps and an analog to digital converter. But I may be able to do additional things like implement an LCD with a segment LCD controller, implement a simple touch screen or some touch buttons with the capacitive touch sensing CapSense technology, maybe drive some LEDs or create some lighting effects for status or indication with a PWM, and of course have the Bluetooth low energy communication so that my heart rate monitor can report my heartbeats back to my cell phone or so, all in a single chip, all in a single PSoC 4 BLE IC. And then eventually, you have a tightly integrated system that does your sensing, that does your computation, and does your communication, but it can also do it at extremely low power so that you can have maximum battery life out of these products that you create. And the way the PSoC enables this is by offering you 5 different power modes called active, sleep, deep sleep, hibernate, and stop. And in each of these different power modes, you have various peripherals that are either available or not. And switching between these power modes is extremely easy. You just simply call an API in your firmware to switch from one power mode to the other. You don't have to go through a set of instructions or several lines of code to set up the clocks in a certain way, to set up the peripherals in a certain way, to retain memory or park it in a different location. You call a single API call, and the system does everything else for you in the back end. What's exciting about these power modes, I'd like to maybe highlight a couple of them here. The deep sleep mode, which consumes only 1.3 microamps. At this mode, your CPU is turned off, but your Bluetooth low energy link is kept active. So if your smartwatch or your heart rate monitor product has established a connection with the host cell phone, it does not have to disconnect from it when it's in the deep sleep mode. It won't be sending any data, but it maintains the connection while it's in this deep sleep mode, and it can periodically wake up, like a heart rate monitor, say for suppose wake up every 1 minute or every 5 minutes to send the information back to the cell phone and then go back to the deep sleep mode. But what deep sleep allows you to do is to maintain that connection with your host so that you can, on demand, immediately send data to it using an active mode. What's also interesting and exciting about the deep sleep mode, under the analog peripherals, you'll notice that many of the analog blocks like comparators and op-amps are available and fully functioning in this deep sleep mode, which means your sensor interface, again I'll use the example of my heart rate monitor, can continue to condition my signal at all times, even when my chip is in deep sleep mode. So when I need the information from that sensor, it's available to me on demand. It's already sitting there in a well-conditioned state for my ADC to pick up, convert into a digital value, and send to my host cell phone over a BLE wireless link. So that's a very, very, very useful mode, and the wireless link here is enabled by a watch crystal oscillator, which is a 32 kilohertz crystal. You also have a couple additional modes that are great for extremely low power consumption. The hibernate and the stop mode that go down to the tens of nanoamps, 60 nanoamps in the stop mode and 150 nanoamps in the hibernate mode. Now in these modes, you do disconnect your Bluetooth connection between your two devices, but the chip is consuming extremely small amounts of current. So this is great for a case where you may not be sending data by the minute, maybe by the hour or so. For instance, if I have a sensor in a room where I'm trying to measure its temperature, I might not care for minute-by-minute updates. I could spread that over some further intervals, and in that case, not worry about taking the extra few milliseconds to establish a Bluetooth connection. Or in another example where my product is manufactured and deployed out of my factory with the batteries inserted into it, but it's sitting on a retail shelf for a long time, and I don't want the batteries to drain out when it's just sitting in this extremely low power mode. This is where stop mode can be extremely useful. The system is essentially shut off, but its battery is plugged in, and it's ready to come back to life very quickly within 2 milliseconds, and it can stay on a battery for a really long time by consuming only 60 nanoamps. So I guess the lesson here, or what's interesting to note here, is IoT products and their battery life and their power consumption is not driven by how much current you consume in your active power mode, but rather by how little current you can consume in your low power modes. Because in reality, the way these systems are designed, they spend very little time, maybe 1/10 of their time in these active modes where they read the sensor data, get the latest condition data and send it over a Bluetooth link. But they spend maybe 80 to 90% of their time in these intervals of sleep modes where they're waiting for the next data to be refreshed, or they're waiting for the next call from the Bluetooth cell phone to provide it updated data. And so by exercising your low power modes and spending maximum amount of time on those, you can greatly impact your battery life. You can change your battery life on a product from 3 months to 12 months by intelligently and carefully using and exercising these low power modes as opposed to keeping your product in an all active mode at all times. So moving on, Cypress not only offers a BLE IC or silicon, but also offers a fully certified and pre-qualified BLE module. A module essentially means a combination of a chip, an antenna, crystals, and all other passives required for this to be a completely ready to deploy plug-and-play sort of system. So our BLE module, which is called the EZ-BLE PROC module, is available in an extremely small form factor. It's only 10 millimeters tall by 10 millimeters wide by 1.8 millimeters in height. So it's got a great footprint, which includes a shield. It exposes 16 GPIOs in this module, which is available in a 21-pad SMT form factor. It has features, several of the features like CapSense, all of your digital communication protocols, your timers and counters, and it allows you to save the time and the cost that you would otherwise need to do if you were taking a chip and then adding your own antenna to it, adding your own crystals to it, because you would have to go through the certification and qualification processes from both the Bluetooth SIG and various regulatory authorities like the FCC, CE, and so on. So modules are great for people who are looking to create the products in minimal amount of time or with minimal investment of board and hardware design resources. What's unique with Cypress's solution is that not only do we design our own chips on our own silicon, we also fabricate them here in the States. We also package and assemble our chips using our own proprietary technologies. We develop our own software tools, including our Bluetooth stack and our development environment called PSoC Creator. And then we also offer design and manufacture of our own modules. This makes us very unique in the industry as the only supplier, the only semiconductor supplier today that offers a true end-to-end Bluetooth low energy solution, all the way from silicon to software stack to module manufacturing. Most module manufacturers today use silicon from different companies. Most silicon companies today rely on third-party module makers to create their modules, which causes problems sometimes, because if you have, and you're doing a development phase, let's say you're using a module from a given vendor, you have certain issues with the software stack or certain issues at the silicon level. The module vendor is not able to provide you that support because they don't own that part, they don't understand how it works, and you may have to work through 2 or 3 levels or 2 or 3 different companies to get your issues resolved. And vice versa with the chip vendors, they aren't able to offer the support of why a module may not be performing in a certain way up to certain performance specs or so on. Cypress has that unique advantage where we have the end-to-end expertise because we do everything in-house all the way from silicon design to software implementation to module design and manufacturing. With the module, this is just a slide that tells you what qualifications and certifications our module offers. So there's 2 aspects of it that you need to worry about. One is your solution, your end product has to be qualified by the Bluetooth SIG or the Bluetooth Special Interest Group that gives you a stamp of approval saying, yes, your product meets all the spec requirements to be called a Bluetooth Smart product. So our module and our silicon is pre-qualified by the Bluetooth SIG. You don't have to go back through the qualification process. You can simply refer to Cypress's qualification ID when using our module or our chips, and you save all of that time and money and that effort. The second thing you have to worry about, and this is true when creating any sort of wireless system, you have regulatory authorities to work through and get certification and permission from before you can legally sell your product in certain markets. For instance, in the U.S., it's the FCC that governs these regulations. You have the IC in Canada. Japan has its own. Korea has its own. The European nations have their own. So again, Cypress's module is pre-certified by all of these regulatory authorities. You have an ID to refer to. This is something that costs over $200,000 if you have to do it yourself. So as a low volumes manufacturer or a smaller company, this often becomes prohibitive for a lot of people, which is why using a module is another great way to not worry about these things, not spend the time, not spend the money, and get to market really quickly. So now that I've talked to you at a high level about the chip advantages and the module, this is a architectural block diagram of the PSoC 4 BLE chip and the things that it has inside of it. If you look at this block diagram on the right side of your screen, and I'll start from the top left, again, of course, you have the ARM Cortex-M0 CPU, which is clocked at 48 megahertz, a great high-performance CPU, which has a good balance between performance and efficiency in terms of power consumption, and it's excellent for computing sensor data that's coming out of these IoT products. The BLE subsystem is obviously fully integrated into this chip. The Bluetooth controller, the Bluetooth balun, all you need to do is hook it up to an antenna, and you're ready to go to communicate wirelessly. The chip includes 256 KB of flash and 32 KB of SRAM. It is also available in a 128/16 KB version if you're interested in that. On the programmable analog front, as I mentioned, this chip has 4 op-amps, one SAR ADC which can sample at 1 megasample a second at 12-bit resolution. It has 2 low-power comparators, and it has a capacitive touch sensing block to implement your user interfaces like buttons, sliders, and touchscreens. On the digital side, the chip has 4 timer counter blocks that can be used as timers or counters or PWMs. It has 2 serial communication blocks that can be used to implement serial communication protocols like I2C, SPI, or UART and help communicate with other chips that may be in your system. It can drive segment LCDs, and previously I had mentioned this chip also has its own integrated digital fabric, which is CPLD based. In Cypress language, we call that UDBs, or Universal Digital Blocks, and you have 4 of these Universal Digital Blocks available inside the PSoC 4 BLE chip, available for you to do any sort of additional digital logic or combinatorial logic in the system. And finally, to wrap things up, the chip is available with up to 36 GPIO, all of them that are CapSense capable, or all of them that can be used as analog inputs or digital outputs. All of the IOs are configurable. Keep in mind, though, that the module that's available today only offers a 16 IO version. The chip offers a 36 IO version. The chip is also available in a couple extremely small packages. Recall the module was 10 millimeters by 10 millimeters X by Y. The chip is available in footprints as small as these 68-pin CSP or chip scale package, which is 3.5 by 3.5 millimeters. So if you have the expertise in doing your own antenna design, or if you're creating a product that is extremely small form factor, the module may not be the right bet for you. You may want to go with the chip and create your own extremely small antennas. And again, that's something Cypress has the expertise in doing, and we can help you through that process. The key point here being that the chip is available in extremely small packages, allowing you to create small PCBs. And here's just a couple examples of the kind of things you can build with this one-chip solution. Here's just a simple fitness monitor, going back to that Jawbone or Fitbit pedometer example that I gave earlier. Something as simple as a step counter or a little more sophisticated that could also measure my temperature, maybe skin humidity and sweat, and also keep tabs on my battery life while still communicating Bluetooth Low Energy and maybe driving a vibration motor or some LEDs. All of these things can be integrated into a single PSoC chip, so you can have a product that truly is a one-chip solution. Here is another example of a slightly more sophisticated and complex system, like a heart rate monitor. This would exercise all of the things like the fitness monitor on the previous slide did, but additionally it would have a sophisticated analog front end to create a heart rate monitoring interface. So instead of buying a heart rate monitor sensor, you would implement a heart rate monitor sensor using the analog circuitry available inside a PSoC, so your BOM cost is highly reduced, and you're again able to create a much more sophisticated product with this one-chip solution. So to wrap things up, here's how you can get started with PSoC for BLE for those who are interested. You can download the PSoC Creator IDE, the development environment, free of cost from cypress.com/creator. You can buy a Bluetooth Low Energy Pioneer kit or a hardware development kit from Cypress for $49. And this dev kit includes a baseboard that's also Arduino compatible, by the way, which is great for prototyping because you can add shields of all sorts of different forms that are available on the internet for some quick prototyping. And it includes a couple of BLE dongles and modules as well. And we have an excellent Getting Started application note called the Getting Started with PSoC for BLE that walks you through all of the basic steps of how do I work with this, the tools, with the chip, with the IDE, and create my first Hello World-like example on using Bluetooth Low Energy. And here's a few more details on what the dev kit looks like. This kit is being held vertically right here. You'll observe on the top right corner is the PSoC for BLE module that's plugged into this baseboard and has a chip antenna on top. All the way on the bottom you notice a USB connector, which is provided so that you can use the baseboard's built-in programmer and debugger to program the chip and to step-by-step walk through each line and debug it. You don't need any external programmers. The I/O headers on the left and right side of the board are in the Arduino form factor compatible shape, which means these Arduino shields that are freely available in the market can be easily purchased and plugged into this kit. Things like sensors, motors, displays, lights, so on and so forth are very easily accessible. And then on the top right of the dev kit, you see a capacitive slider. It's a 5-element capacitive slider that can be used for left and right slide gestures, or maybe even as 5 independent buttons. So you can implement your user interfaces for your product with that capacitive slider. In addition, the kit has a few more things like a couple push buttons or switches, an RGB LED for some lighting and dimming. And on the rear side of the dev kit, not shown in the picture here, is a 3.3 volt coin cell battery holder. So this entire development board or this entire hardware unit can be powered with a single CR2032 standard off-the-shelf coin cell battery that operates at 3.3 volts. So you can design a system that's extremely low power and also validate that by running it off of a battery as you're doing your development. And with that, I'm at the end of today's presentation. I'll leave this slide up here with references and links that are useful to find more additional information about this solution.
Great. A few of you have already submitted questions, so we're going to jump right in.
Okay, excellent.
Into the question window on the side of your screen, and then hit the submit button. While we're answering questions, we'd like to ask you to complete the feedback form, which is located on the right, or on your widget bar. So for the first question, Is the EZ-BLE available all set up to do BLE to UART right out of the box?
So the EZ-BLE is available in two ways. One way where the BLE stack is exposed to you, the user, and you can implement your own profiles and your own topologies on it. And then it's available in a second form factor where it is simply a BLE to UART module where you don't have to worry about developing with it in PSoC Creator. You just communicate to it over UART and configure the entire BLE stack and profiles over UART. So both options are available, yes. Good question.
Okay. For the next question, what size and footprint is the EZ-BLE PROC module available in?
Okay. The EZ-BLE PROC module is available in a 10 cross 10 cross 1.8 millimeter footprint. So it's 10 millimeters wide, 10 millimeters tall, and 1.8 millimeters in height.
Okay. What version of the BLE stack does Cypress Solutions offer?
Currently, the version that is in production is compatible with the Bluetooth spec version 4.1. By the end of this year, we will have qualified an upgraded Bluetooth version 4.2 solution. 4.2 is interesting because the spec adds a couple new features to it, specifically in terms of some privacy features, some extra security features, and also some data length and packet improvements so that you can actually transfer more data, in fact up to 250% faster data transfers in Bluetooth 4.2. So our Bluetooth 4.1 is available today, and Bluetooth 4.2 is expected to be qualified before the end of this year and be available.
Okay. Does the BLE stack utilize onboard flash? Typically that's about 128 or 256, depending on the chip.
Yes. Another good question. So as you recall, this chip is available in two memory footprints, a 256K version and a 128K version. The BLE stack consumes portion of this flash. Depending on how you configure your BLE stack, which is specific to your profiles, it can consume anywhere between 70 to 80 kilobytes. So on a 128K chip, you're still left with about 50 or 60 KB of flash after the BLE stack has been implemented. But on the 256K, you have another time and a half space of flash available, which is excellent because it can be used to create some really intensive applications, or if you can create your entire stack plus application inside the 128K, you have another 128K remaining to perform over-the-air firmware upgrade. And that's a really important feature in several of these Bluetooth products because once I deploy my product in the market, I'd like to be able to wirelessly bootload it or wirelessly upgrade its firmware and provide new features or functionalities or bug fixes to my customers. So the 256K is extremely useful for that. It gives you that additional 128 KB of flash so you can store a separate image and use it for over-the-air firmware uploading. And Cypress provides all of the tools to do over-the-air firmware uploads in terms of projects, example projects, and even a mobile app, so I can do my firmware upgrades as easily from a cell phone.
Okay. The system can be used as a BLE device, but can it also act as a central device and essentially scan for other BLE devices?
Absolutely. So once you drag and drop the BLE component in your PSoC Creator schematic, you can pick and choose how you want your BLE gap or GAT configured. This device can be configured as a peripheral, which is the most common use case for, let's say I am a fitness monitor. I'm a peripheral to a cell phone, so I'll be providing information to it. But it can also be configured as a central, where it can be listening for connections from other devices and be that host, that central host device. You can also configure it in a mode where it does a little bit of both. It switches roles between a central and a peripheral depending on what mode or situation it is in. So I guess the short answer is yes, you can absolutely implement a BLE central device with this as well.
One of the new things that is popular are Bluetooth beacons. Can the BLE module implement this?
Yes, absolutely. Good question again. Beacons are really good and very popular. The specific mode that a Bluetooth Low Energy beacon operates in is called a broadcaster. So as I just talked about, peripherals are devices that have some information and will connect to a cell phone. A central is the host device that will allow other peripherals to connect with it. A broadcaster is kind of like a peripheral because it has some information that it's sending out, but the difference is that it does not actually establish a connection with any other device. It just provides information in its broadcasting channels, and that information may be as simple as, hey, I am a node and I am here, or here's my temperature, or here's a URL. This is very common in retail applications where kiosks are being outfitted with these beacons, and they can be used for indoor navigation and tracking or for enhancing product information as I walk up with my cell phone to a retail kiosk and I can get more information about that particular kiosk to send over to my cell phone. So these are being done via beacons, and yes, you can implement a beacon or a broadcaster device with PSoC for BLE. In fact, we have a couple example projects that help you how to create an iBeacon, which is Apple's version of beacons technology, or even Eddystone, which is Google's version of beacon technology.
Okay, moving into antenna design. Will PSoC help with the antenna design? And sort of a follow-on question, will PSoC provide a software package to design and validate the antenna design and simulate it? And one that I'll add to that is you still need FCC approval for these types of antennas.
Yes, so answering the questions one by one. Cypress, so to get things started, Cypress has an excellent application note that is dedicated to antenna design and how to create the best possible antenna design for your applications. And if you go back through the slides, through the references, you'll notice that link to the antenna designing application note that has all of the details. In addition, the antenna designs of the PCB antenna that we have implemented in our development kit that you evaluate with are freely available to all users. You can download those schematics, and feel free to reuse our antenna designs because our antenna designs have already been qualified by the FCC. So you have a very high degree of confidence that if you repeat or copy our antenna designs, and feel free to do so, you will pass FCC qualification with very little issues. And then the third aspect of it is does Cypress provide support in terms of antenna design if you're trying to do something unique and special to your design, your product, and your application? Absolutely, we do. Cypress has an excellent technical support system that's offered via a ticketing system on our website or via telephone support where you are engaged and assigned to an engineer who's working, helping you through your product and your application. And we do have antenna experts in the company who on a case-by-case basis can help you with your specific antenna design issues if you come to that stage.
Okay. Here's a more general question. What do you think is going to be the quickest path to evaluating PSoC?
Great question. I would say, go back to slide 25 where I had the information on how to get started. You have, 3 simple steps, which is you can download the IDE or the development environment for free. It doesn't cost you anything, and you can start playing with the projects. You can start playing with examples that people have done to kind of get your feet wet with PSoC. The minute you're ready to start doing something on your own, you can buy that low-cost $49 development kit, which is really fun to play with even otherwise if you want to learn how BLE technology works. So with the combination of the IDE and the development kit, and then third step being the getting started app note, which really easily eases you into how do I get started as a brand new user. that would help you get started as the quickest path to evaluate PSoC for BLE.
Okay. This has been primarily talking about the hardware and a little bit about, the software stacks. But what about the development side of things from Cypress? Include things to track power utilization and things of that nature, which are going to be very important in IoT type applications.
Yeah, great question and very important indeed. As I mentioned earlier, power consumption has become one of the most important factors in these IoT products because it's what differentiates often enough a good product from a bad product. Consumers have been complaining about the first generation IoT products not providing enough battery life. So at a chip level, I talked about how we have these 5 different power modes and how you can exercise them intelligently to maximize your battery life for your product. And there's a couple things Cypress does to help you with that. Firstly, we take pride in writing our documentation, and just like the antenna design guide, we have an application note dedicated to power consumption and power reduction techniques. So you have a detailed application note that teaches you about all these 5 power modes, that gives you examples of how to use them, shows you how to use them with example projects and code, and really talks about the intricacies of things and tips and tricks that you can do to best utilize these power modes, to extract maximum benefit from them, to eventually create your product with best battery life. So again, if you go back to that references slide, I believe that application note for power consumption techniques is also included there. And if not, you can do a very easy search for it on cypress.com and find that answer or that application note. Additionally, on the development kit, since power consumption is a very critical factor, and we've gone ahead and included the coin cell battery holder, so you can actually plug in your battery and do your development off of battery rather than being plugged into the wall. We also have a special jumper on the dev kit that's dedicated to measuring power consumption of the chip. It isolates the PSoC 4 BLE chip that's on the dev kit from all of the other things that are on the dev kit, isolates it. You can stick a picoamp meter, for instance, across that jumper, or a simple ammeter, depending on what types of currents you're measuring, and see your real-time power consumption as your product is being developed and being debugged. As you switch between power modes, you can see in real time what your ammeter is showing for power consumption. And the reason you'll need that picoamp meter is if you're really trying to exercise some of those stop and hibernate modes where the chip is down to the tens of nanoamps, you're going to need a pretty sensitive meter to measure them. But the short answer is we have an application note that teaches you how to optimize power consumption, and then there's a special jumper on the hardware kit so you can, in real time, see what your power consumption is.
Okay, this question I think is along the same lines, but I'm not sure you had answered it. Is it possible to determine the sleep power consumption based on the number of active analog blocks that are configured? In other words, I think it's more from the configuration end as making an estimate as opposed to runtime.
I'm sorry, can you repeat that question for me? I was just looking for it in the list to make sure I understood it correctly.
Okay, it's about halfway down, but essentially if you have a selected number of analog blocks in the system, can you estimate the amount of power in a particular mode, like the deep sleep mode?
Yes. As part of the power measurement and optimization application note, there's also an Excel file that's available where you can plug in some numbers into that Excel file, and it acts as a little calculator to give you a theoretical estimate of what your power consumption would be in those modes. In addition, if you look at the chip data sheet for PSoC 4 BLE, each of the blocks is characterized. Each of the IP hardware blocks that's inside the chip, like the op-amp, like the ADC, like the timers, PWMs, and even the comparators, have electrical, AC, and DC specs defined in the data sheet. You can look at those specs, and this is a chip that's been through a full characterization process, so we guarantee those specs. By looking at the specs, you can look up a simple table and say, okay, I know my op-amp consumes maybe this many micro to milliamps in these modes under these configurations, and you can use that knowledge and that data to plug it into a simple Excel sheet and determine what your power consumption should be, and then you can validate it by actually measuring the power consumption of the chip.
Okay. Is the ROC module BLE certified already, or does it have to go through certification if you're going to be using it?
Yeah, so the PROC BLE module, as I showed in slide 21, I believe, has full certification, global certification from all of the regulatory authorities like FCC, CE, JRL, so on, and it has pre-qualification from the Bluetooth SIG. So it's fully certified by regulatory authorities for its RF portion, its wireless portion. It's fully qualified by the Bluetooth SIG for its Bluetooth compliance and compatibility. As an end product, you will still need to get a simple certification from the Bluetooth SIG that gives you the permission to brand your product as a Bluetooth smart product. But it's greatly simplified because for 3 out of 4 things you refer back to Cypress's for your end product, Cypress's qualification ID. For your end product as a whole, you have to pass through very simple steps and tests on the Bluetooth SIG. Similarly, with the regulatory side of things, if you don't touch the antenna design and maintain it as is, you can reuse Cypress's FCC ID for regulatory certification on the wireless side of your design. There may be other parts of your or other portions of your system separate from this that may still need to go through FCC certification, which is fairly common for all consumer electronics or electronic products sold in the USA. But the wireless part of it is greatly simplified because that is pre-certified and you can use Cypress's ID.
Okay, I think you answered this when you were talking about the BLE stack, but is the ARM core shared, essentially used to run the BLE stack, or is it independent? Or is there an independent core for the BLE support?
This ARM core is a single ARM core. It is shared with all of the peripherals and the BLE stack. It does the management and the time sharing between the Bluetooth part of the system and the rest of the peripherals that are in it. But the CPU, which is the ARM core, and the flash, up to 256K available, are shared for your application and your Bluetooth low energy aspect of the system.
Okay. You talked before about the consulting and help services, but can they also be used for actual product development?
Yes, Cypress and Cypress partners offer all sorts of different channels to help you with the product development side of if you need that. Cypress officially has something called Cypress Design Services, which under certain cases may work for both of us, for you and for Cypress, where Cypress helps you with product development. But what's probably easier and much quicker, because there's a lot more, is Cypress certified consultants around the world available, and these are listed on our website. Consultants and third parties who go through our certification process and are guaranteed by Cypress to be qualified in knowing how to use our technology and our products are available to help you develop your end products using Cypress chips like PSoC. And a list of these are available on our website. What might work best for you is finding the one closest to you, or in your geographic location, or the one with the right expertise and combination of skills required for your specific project. So short answer, depends on the specifics of your project, but yes, a couple different options are available both inside Cypress and Cypress partners.
Okay, I think this has more to do with how BLE operates in general, but if you have a device, how can you save power if it's always advertising itself? I'm not sure if that's really the case.
One more time, sorry. I just want to make sure I understand that question again.
essentially if you have a BLE device, is it always going to be advertising itself, essentially the radio always being active?
Good question. Yeah, I understood the question. So the advertising timing settings are essentially what we call in the BLE stack, the advertising parameters are configurable within certain specs as defined by the Bluetooth Low Energy spec. So you could have a device that's advertising as fast as every 8 milliseconds, which I believe is the low end of the spec. So something like a beacon or a broadcaster would probably want to do that. It's always advertising. But you can also, at the lower end of the spec, turn that advertising down to very slow rates, as slow as once every 4 seconds. So if you have something like a temperature monitor in your bedroom where you don't really care for the change in temperature every 4 seconds, that lower end of the spec can be used. It can be, and to configure that, it's a simple, type in 7.5 or 4000 in your BLE component GUI, and it generates the right code to configure the advertising parameters on the stack that way. And of course, the lesser you advertise, the less communication you're doing over the Bluetooth radio, the lesser power you will consume, the more battery life you will have. So these are some of the tricks and things you can do to influence battery life. I don't always have to be the fastest communication or always advertising or always transferring. I can slow down some of those things or provide greater intervals between some of those things like advertising or data transfer to get better battery life out of my product.
Okay. We have a number of questions, but we'll wrap up with this last one. We'll answer via email any of those we didn't get to. I think I'll sort of extend this out. From an FCC point of view, what do you have to wind up certifying? For example, I think we talked about the PROC module. That's one piece. Another would be if you are using this on your own board, do you have to certify the board, the system, or just the antenna? How does all that work?
So a couple things. If you use the PROC module, which is pre-certified by the FCC for its wireless side, wireless portion of it, and then you simply plug that into your system, you don't have to recertify the wireless side. But as I mentioned earlier, in most cases than not, you may still have to recertify your entire system as a whole because it may be doing other things which is outside of the realm of the PROC module. And at that point, you will need to go through your own independent FCC certification depending on where, what geographies you're trying to sell the product. But you can go back and reference Cypress's pre-certification on the FCC part for the wireless aspect of the design. So when using the module, the pre-certified module, life becomes a lot easier with the FCC guys. If you're using just the chip and creating your own PCB antenna, you don't have a choice, but you have to go through FCC or regulatory certification. And the recommendation there is to use a Cypress prescribed design that we know has passed FCC qualification in other cases, so it'll make your life easier. You still have to go through the process and spend the money, but you'll have less reworks. You may get through the process on the first time rather than doing it 3 or 4 times over, and you have a known good entity of a design to start with.
Great. Well, that concludes today's presentation. On behalf of Electronic Design, I'd like to thank you for joining the webcast today. Thank you to Cypress and Digi-Key for sponsoring this event for us today, and have a productive remainder of the day.